So superconductivity was first discovered by a gentleman known as Camberling Ons. Okay, so superconductivity was discovered, okay, in 1911 by a gentleman Camberling. Okay, okay, Camberling Ons. Okay, so he wanted to measure the resistivity of mercury, okay, pure mercury at low temperature. Okay, so superconductivity is not something which occurs at ordinary temperatures. Okay, in order to see superconductivity, you require low temperature. Okay, in fact, very low temperature. Okay, so these low temperature can be produced by liquefied helium. So before he measured the resistivity of mercury at low temperature, first he produced low temperature, okay, by liquefying hydrogen. Okay, so let low temperature, okay, by liquefied helium. Okay, so liquefied helium has a temperature of 4.2 Kelvin. So when he was measuring the resistivity or resistance of mercury, okay, so what he observed, pure mercury. Okay, so you observed at T is equal to Tc, okay, equal to 4.2 Kelvin. Suddenly the resistivity drops to 0. Okay, so when he measure the resistance, okay, the resistance should be less than 10 raised to power minus 5 ohm. So the zero resistance means it is almost zero, which is not measurable by your present instruments. So when we measure the resistivity goes down to zero. This is a sudden transition. Okay, so resistivity drops to zero, okay, suddenly. Now if I compare these features with a normal conductor, okay, so we know in normal conductor also, when we reduce the temperature, okay, so reduce the temperature, conductivity will decrease. Okay, so we know the main reason behind the resistance is what? Your phonon vibration. If you are increasing the temperature, your phonon vibration will increase, and because of this phonon vibrations, your scattering will increase and your resistance will increase. So if you are decreasing the temperature, your phonon vibration will freeze out, and there will be less scattering, and your resistance will decrease. So if we see the variation of resistivity versus temperature for a normal conductor, so they show this kind of behavior. Okay, this kind of behavior means at low temperature the resistivity varies as a T5. Some materials show variation as a T cube or T2 also, but in general normal metals, okay, they show the variation resistivity as a T5. Okay, this is also called Bloch's law. And when you're high temperature, your resistivity increases linearly with temperature. Okay, high means what is high and what is low, that depends on material. Okay, that depends on the Debye temperature. If your temperature is well low than your Debye temperature, then it's called low temperature. Okay, if your temperature is high enough compared to your Debye temperature of that particular material, then that is called high temperature. So in high temperature, your material show resistivity variation as a proportional to T, while at low temperature shows proportional to T5. While when we see superconductivity, this is a normal conductor. It's a normal conductor. Okay. So if I see superconductor, what happens? The resistivity suddenly drops to 0. So this is a superconductor. So this is the difference between a superconductor.
Sir,
बोलिए.
Sir, can you just repeat last 2 minutes of lecture, sir?
So we were discussing superconductivity. Okay, so superconductivity is low temperature phenomena. So when you reduce the temperature of temperature of certain samples, their resistivity drops down to 0. Okay, so this phenomena is called superconductivity. So I'm comparing this superconducting sample with normal samples. Okay, normal conductors. So when you reduce the temperature of a normal samples, okay, so the temperature decreases. Okay, so variation of resistivity with respect to temperature is given by rho is proportional to T5 at low temperature for normal conductors. Okay, and high temperature they show the dependence on T as proportional. Okay, their resistivity of conductor is proportional to T. You increase the temperature, conductivity increases. At low temperature, it is fast. Okay, it is T raised to power 5. So, but while superconductor, if you go in low temperature design, okay, suddenly its resistivity drops to 0. Okay, that difference I was explaining. Okay, so now here it is clear that in superconducting state your resistivity is 0. Okay, but superconductivity is not only about the resistivity. Okay, resistivity 0 is only one thing. Okay, so let me write here that superconductivity, okay, superconductivity implies, yes,
फर्स्ट ग्राफ जो आपने ड्रॉ किया है ना वो मतलब क्या इसका मतलब
this is for mercury, this is for mercury. Okay, this is for mercury. Okay, mercury sample, pure mercury sample. This is for pure resistivity versus temperature graph for pure mercury. Okay, and this is for normal, any normal conductor, and this is for typical graph of a superconductor. Is that clear?
yes sir
Okay,
thank you
so now superconductivity implies several phenomena, not only rho tends to 0, several phenomena. Okay, several phenomena in addition to the fact, in addition to the fact that the resistivity rho drops to 0. Okay, resistivity rho is equal to 0. Okay, so superconductivity not only about resistivity, there are many more properties, because your superconductivity is a thermodynamic phase. Okay, it's a kind of phase transition. So when you reduce temperature, your sample goes from a normal state to superconducting state. Okay, so this is the kind of phase transition. So not only resistivity is dropping to 0, there are many more properties which is going to change. So we'll discuss these things one by one. So can I erase this one?
सर एक मिनट
सर
हाँ, बोलिए।
सर जैसे अपन सुपर कंडक्टिविटी मरकरी सर उसकी तरह कोई और भी मटेरियल होगा जिसमें अपन सुपर कंडक्टिविटी या फिर सुपर कंडक्टिविटी उसका दिखा सकते हैं कि हाँ ये शो कर रहा है कि सुपर कंडक्टिविटी हो गई, और उसकी भी अगर अपन बाय द रेजिस्टिविटी 0 कर दें मे बी, और कोई मटेरियल ऐसा है मरकरी के अलावा?
So this is the zero resistivity is only the one test. If your sample suddenly drops to 0 in particular temperature called critical temperature, then that material may be superconductor. It is not necessary. Okay, because there are some perfect conductors, or there are pure samples. When you reduce the temperature, their resistance also approaches to 0. So superconductivity, zero resistivity is not only one test. Okay, so there is a, if you want to test if a particular material is superconductor or not. Okay, so the true test is Meissner effect. Okay, so if I want to test that a sample, given sample is superconductor or not, then what I can test? Okay, so superconductivity is basically two properties. So superconductivity is basically number one, okay, your rho should be 0, okay, or your sigma conductivity should be infinite, and number two is perfect diamagnetism. Perfect diamagnetism. Okay, that means your material should behave perfect diamagnetic. Perfect diamagnetic का मतलब क्या होता है? The B inside B inside the superconductor should be 0. Okay, B inside the superconductor. Okay, B should be magnetic field inside the superconductor should be 0. Okay, now we know the magnetic field is given by mu0 H external plus magnetization. Okay, now because inside the superconductor B is 0. Okay, so if I calculate, this will be my H external plus M, and if I calculate the susceptibilities, okay, and susceptibility will be by M by X. Okay, so this should be equal to minus 1. In the case of superconductor, this susceptibility should be equal to -1. There are two tests. Okay, one, you have to measure the resistance. Resistivity goes to 0. Then you have to test whether it is perfect diamagnetic or not. Okay, your sample should be perfect diamagnetic. Okay, and this effect is called your Meissner effect. Okay, so this effect is called your Meissner effect. Okay, so what
it means this chi should be equals to -1.
Chi should be -1. Okay,
Then
so
it is known as Meissner.
then it is superconductor. Resistivity goes down to 0 plus your chi should be -1. Okay, what does this mean? So if I have a sample, okay, so what is Meissner effect? Okay, so if I have a sample, if it is in the magnetic field, so magnetic field line will penetrate inside the sample. Okay, when my temperature T is greater than Tc. So superconductivity transition happens only at particular temperature. So when you are a sample, if temperature is greater than Tc, then this will behave like a normal conductor. Okay, now once you cool the sample, okay, when you cooling, okay, and your temperature is less than Tc, in that condition what will happen? All the flux lines which were penetrating inside, they will expel out, they will come out. So all the field lines will be come out. Okay, so this is your Meissner effect. Okay, so when temperature, so this is B inside. Okay, so we have some B inside, we have some B inside. Okay, here what we have, B inside equal to 0, B inside equals to 0. So the magnetic flux line expel out. Okay, so when your T is less than Tc, magnetic flux line are completely expel out. That is your Meissner effect. It is clear?
The expel out means
बाहर निकल जाती है,
inside में
जीरो है.
नहीं जा पाता है.
Your magnetic field not able to penetrate inside the this
Metal
superconductor.
conductor.
Okay.
Yes, sir.
Now if your material is have perfect conductivity, okay, suppose you have material which have very high conductivity, in that case also your B cannot penetrate inside. Okay, so what is the difference between a perfect conductor and superconductor? Okay, so I hope my question is clear to you. If you have you must have read in your EMT course. Okay, if your material is infinite conductivity, okay, perfect conductor, then your magnetic field cannot penetrate inside this one. And same thing is happening in superconductor also. The flux is coming out. So that's why I told you zero resistivity is not the true test. True test for superconductivity is what? Your Meissner effect. If your material is showing Meissner effect, that then only you can say it is a superconductor. So what is the difference between a perfect conductor, this perfect conductor and a superconductor? Okay, so let me explain this, the difference between a perfect conductor and superconductor. Can I erase this one?
Yes, sir.
Yes, sir.
Yes, sir.
Now put the heading perfect conductor versus superconductor. Okay, so perfect conductor okay, and you have superconductor. Okay, now suppose I have a sample, a ordinary sample. Okay, so for this ordinary samples, okay, I'm keeping b is equal to 0. Okay, so in this sample I'm not applying any magnetic field and my temperature is T is greater than Tc. Okay, now I have same samples, the sample of same material. Okay, and my temperature is T greater than Tc and I'm applying magnetic field. Okay, so this is a normal sample. Okay, it's a normal sample. Okay, so this is the perfect conductor. Perfect conductor का मतलब क्या है? When you will reduce the temperature, this will become perfect conductor. This conductivity goes to infinite. Okay, here perfect conductor means what? This is a pure sample and you're cooling. When you're cooling, it is becoming more and more conductor. Its conductivity keep increasing. So at low temperature, it becomes almost infinite material with infinite conductivity. So now what I'm doing, I'm cooling this sample. Okay, so I am cooling below Tc. Okay, so cool below Tc. Okay, so I am cooling this sample below Tc. Okay, so what will happen if I cool the sample below Tc? Okay, so here is a normal sample. Okay, and your normal sample, it obeys Maxwell equation as it is. Okay, so what is the Maxwell equation? So you know the Maxwell equation, you have del cross E equal to minus del B upon del T. Okay, or this is the differential form of Faraday laws. Okay, if I write in other form, so I can write E dot dl is equal to del phi B upon del T. Can I write like this?
Yes, sir.
This is the Maxwell equation. Okay, third law of Maxwell equation. Okay, so this is the electromotive force. Electromotive force is nothing like line integral of your electric field. Okay, and electromotive force is equal to the rate of flux change del phi upon del T. So this is these are Maxwell equations, and these Maxwell equations are followed by normal conductor. Okay, so when I'm cooling below Tc, okay, so this material become perfect conductor. Okay, perfect conductor means now electric field cannot penetrate inside this one. Okay, so what is the property of perfect conductor? Okay, it will shield outside electric field. So when I'm cooling this one, okay, this E will 0. So this electric field will be 0. So once this electric field is 0, your flux should be, when this E is equal to 0, your phi B should be constant. Okay, so when I'm cooling, the flux penetrating this conductor should not vary. Phi B should be constant because of this temperature E is 0. Okay, so now if I write this sample, so this sample we have a B0. Okay, and this sample will be also as it is. No flux line will reduced. Okay, or no there's no increase in flux lines or not reduction of flux lines. Okay, so this is your condition is below when T is less than Tc. Okay, this is the T less than Tc. Now suppose I am applying some B. When the temperature is reduced, I am trying to apply some magnetic field in the sample earlier which was 0. So now I'm applying some B. So what will happen? if I apply some B, okay, suppose I'm applying some B applied field now. So what will happen?
It will be expelled out.
Why?
So because temperature is below TC, critical temperature.
But this is a normal conductor, not superconductor. This is also normal conductor. Huh.
Sir, it
So
will
magic-
field lines will pass through the material, I think.
No. So this case also, I told you, when it is perfect conductor, E is 0. E is 0 means the flux cannot change. So it was like this, it will be keep like this. Now if you apply magnetic field also, B is 0. So if you so field cannot change. So earlier field was 0, so it will be 0. There was no flux line. The flux was 0. So it will be the same 0 now also. Okay. So even if you try to apply some B equal to B magnetic field, okay, this will not penetrate. I hope this point is clear. In normal conductor or normal conductor, not normal conductor, it is a perfect conductor. So in the case of perfect conductor, if we cool below, when this conductivity become very high or close to infinite, okay, and that time also if we try some magnetic field, we try to penetrate some magnetic field, it will not penetrate. Okay, and if is there already magnetic field, it will also exist inside because flux cannot change. Okay, this is your perfect conductor. Okay, now what happens if I make B is equal to 0 in both the case below TC? Okay, now I have this case. Okay,
Sir,
हाँ
sir, here you are discussing cases कि एक में B 0 है और एक में B है, तो after TC,
so after
below TC में क्या
so
होगा?
I have earlier I was what T is equal to TC. एक में one sample already have field, other sample do not have a field. When I'm cooling that one, field remain inside. Field remain inside means flux. Their flux they should not be changing flux. The flux is inside. Flux is not changing. Flux is constant. Okay. And in second case, if in T is less than
B
TC
0,
and I'm applying magnetic field, it will not penetrate inside. It will be keep outside. Okay.
okay, sir.
Now if I'm now in this second condition, okay, when T is TC, now I am again making B 0. So what will happen if I make B 0? So what will happen now? Here B is there. Okay, B is equal to BA is there. Here also B equal to BA there. Now I am making external field 0. So what will happen? The flux should not change. Okay, because this is a perfect conductor. So nothing will happen in this sample because you're making B 0. All the lines will go out, will disappear because earlier it was inside also 0, now also 0. So this sample will change nothing. But what about this sample? Okay, now you are reducing B equal to 0. Okay, so when you make B equals to 0, okay, the flux should not change. Okay, but you have made a B 0. So what will happen? Now there will be current will be generated. Okay, current will be generated inside the sample. Okay, current will be generated. Current will be generated to maintain. Current will be generated to maintain the same flux. Same flux. Okay, so this is the case of your perfect conductor. Now we'll see how superconductor behaves. Yes.
ये जो
Sir,
हमने
also
दो
direction should be opposite, no?
Yes,
Direction of-
yes. Yeah. This should be this one. Okay.
due to Lenz law.
Yeah. But B will be your constant. Okay. The linked flux will not change in this case. There will be current will be generated inside the conductor, perfect conductor, and flux will not change. Okay. Now let me explain how it is different from your superconductor. Okay. Shall I erase this one? I hope this point is clear to you. What I have done
Sir,
with perfect
sir.
conductor. Yes.
Sir, in this case, sir, can you explain once more? This last point, sir.
The last point, what I said, because it's a perfect conductor, conductivity is infinite, your flux cannot change. due to Maxwell equation. Now you are changing B, you're making B applied to 0, you're making B 0, but flux should not change. So this line there should be same flux. So, but you have made the B 0. So this flux line should have to disappear, because this flux line is B. So what will happen? The material will generate its own currents that will maintain the same flux inside this conductor.
Okay, sir. Thank you, sir.
Okay.
So meaning that ki whenever V is 0, still we have some flux, like constant flux.
Yes. In the case of perfect conductor.
Okay.
Okay. That's why it is not a perfect diamagnet. Okay. Superconductor. I told you superconductor is perfect diamagnet. In any situation, there should be zero. There should be a zero magnetic flux inside. Okay. But in this case, okay, even you remove the magnetic field, your temperature less than Tc, but you have some memory. Okay, so you have some flux inside. Okay, so your perfect conductor is showing zero resistance, infinite conductivity, E is equal to 0, but it is not your perfect diamagnet. Okay, so let me explain now what happens once you use superconductor. Same thing. Okay. So superconductor generally do not follow your Maxwell equation as it is. Okay, we can apply Maxwell equations and get some idea only. Okay, so let me explain now this for superconductor. Okay, so I have a superconductor now. Okay, now I am applying same thing. Okay, I am taking 2 samples. Okay, so I have 2 samples. Say these are superconductor samples. Okay, so B is equal to 0. Okay, and T is greater than Tc, and I have one more sample. Okay, where I'm applying B is equal to B applied. So now flux line will penetrate, obviously. Okay, flux line will be inside. So because this is a normal state. Okay, even though this is superconductor, but it will happen. It will show superconductivity only when temperature is less than Tc. Now when we are cooling this one, okay, cool below Tc. Okay, so let me write here now. Okay, so cool below, cooling below Tc. Okay, so what will happen? This sample will be remain same. There is no field. Okay, and this when become T is less than Tc. Okay, all the flux line will expel out. That means your sample will behave like perfect diamagnet. Okay, that means your chi is equal to -1. Okay, so it will behave like a perfect diamagnet. Okay, now what happens if you apply this B applied here? If you apply B equal to B applied, again those lines will even T less than Tc. Okay, these lines will not penetrate because it's showing infinite conductivity. Okay, so that will be no change in this. Okay,
So what you written inside, please show.
this is your perfect diamagnet. Perfect diamagnetism. Okay, that is your chi should be equal to -1. Okay, now what will happens if I remove the B? अब क्या होगा अगर B रिमूव कर दूं तो क्या हो जाएगा? Okay, if we remove B, okay, if less than Tc, I am removing B, so what will happen? This flux simply go out. If you make B is equal to 0, okay, when T is less than Tc, okay, so this lines will simply go out. This is a difference between a sample, okay, your perfect conductor and a normal conductor. Okay, perfect conductor में the flux change नहीं हो रहा था. When you are going transition, you are going low temperature range, it will kept inside. Here it is expelled. Okay, so this is the difference between a perfect conductor and a superconductor. Superconductor shows perfect diamagnetism. Okay, that is x equal to -1. Yes. Is any question? Okay, now हाँ बोलिए.
सर जो फर्स्ट हम ड्रॉ कर रहे हैं ना B इज इक्वल टू 0, वो 2 केसेस है ना सुपर कंडक्टर के,
हाँ हाँ
मैग्नेट
हाँ
इनिशियल से 0 था।
यस
और सर लास्ट में हमें जो आपने अभी ड्रॉ किया ना सुपर कंडक्टर के केस में, उसमें दोनों इसमें हमें एक्सपेल आउट मिलते हैं क्या मैग्नेटिक फील्ड?
बी इसमें तो एक्सपेल आउट हो गया, ओके
हाँ।
और इसमें पेनिट्रेट ही नहीं हुआ। इवन टेम्परेचर T लेस देन TC है और फिर तुम मैग्नेटिक फील्ड लगा रहे हो, सो मैग्नेटिक फील्ड इज नॉट पेनिट्रेटिंग इनसाइड एंड फ्रॉम हियर इट इज कमिंग आउट।
ओके, सो इन द फर्स्ट केस B इज इक्वल टू 0 हमें ये फ्लक्स मिल ही नहीं रहा है।
हाँ ओके, तो फर्स्ट केस में तो हमको फ्लक्स पेनिट्रेट नहीं कर रहा है एंड हिस केस में बाहर आ जा रहा है, while in the case of normal conductor what we have seen, it is maintaining this B inside. Okay, so this was your difference between a perfect conductor. So that's why I told perfect conductivity resistivity 0 is not the only test. Okay, the true test of superconductivity is perfect diamagnetism. So in objective question, this sometimes they may ask, okay, what is the true test of superconductivity? Then you have to write that perfect diamagnetism is the true test of superconductivity. Okay, now let me write some features. Okay, so features of superconductor, features of superconductor. Okay, what are the features of superconductor? Okay, we have seen number 1, zero electric resistance. Okay, number 2, okay, no change in crystal structure, no change in crystal structure. Okay, confirmed by X-ray diffraction, confirmed by X-ray diffraction. Okay. So superconductivity is not because of some crystal structure phase change. Okay, that thing you have to keep. Yes, if your sample is FCC, it will be remain FCC. Okay, so because of this crystal phase change, your transition is not happening. Okay, that means you're not getting superconductivity because your sample is changing its phase, crystal structure. Okay, so that is confirmed by X-ray diffraction. You take the X-ray diffraction in normal state, you take that X-ray diffraction in superconducting states. Okay, both X-ray diffraction of the sample will become same. Okay, X-ray diffraction is the fingerprint of material. Both will show same sample. That means there is nothing to do with crystal structure. Okay, in superconductivity, that point you have to remember. Okay, in some cases when you apply pressure, then also your samples show superconductivity. In those cases that there will be change of phase, that is not studied so far. Okay, there are some material when you apply high pressure, you can increase TC. Okay, so far you have achieved TC high temperature up to 164 Kelvin. Okay, when earlier we were discussing these superconductor, these are called type 1 superconductor. So their TC was below 20 Kelvin. Okay, below 20 Kelvin, below 30 Kelvin. So in 1986, some new material will discovered. Okay, which can go up to very high TC. So you can because of superconductivity you get this magnetic levitations. You have maglev trains also running now. In Japan is making this these trains. Okay, and it is expected to come on in 1927. I think 2027 they will come in the market. So these maglev trains, okay, this magnetic levitation is because of the superconductor. Okay, because of development of high temperature superconductor. So here I want to say one point clear, there is nothing to do with crystal structure superconductivity. So why, the automatic question is why resistance drops to 0. Okay, you are applying current. Okay, so current is there in the sample, even though their resistivity is 0. So why it is so? Okay, so let me write here number 3. So 0 electric resistance, no change in crystal structure, and okay, it is characterized by okay, number 1, infinite conductivity. Number B, J is finite. Okay, J is finite, तभी तो resistance measure कर रहे हो. Okay, So in superconducting case, you have sample, you are applying current, but it's not showing any voltage drop. That's why we say resistance is 0. But J is always finite. Okay, current density is finite. Okay, see electric field. Electric field is 0. Electric field is 0 in superconductor. Why? Because you know J is equal to sigma E. Now I am saying conductivity is infinite and J is finite. Now both things cannot happen if your E is not 0. Okay, if this is infinite, this is finite. This only happen. So this when your E is fine, E is 0. Okay. So inside the superconductor, you have E0, B0, J0, and one more thing. What is one more thing? B is constant. B is constant, which is equal to 0, in when T is less than Tc. Okay. And one more thing. Okay. The last thing for superconductor, which is most essential, बहुत important. Okay. That is chi should be equal to -1, perfect diamagnetism. So these are the essential features of superconductors. Okay. Now let me discuss. हाँ अभी मैं बात कर रहा था कि resistivity 0 क्यों होती है? Why resistivity drops to 0? Why superconductor do not show any resistance? Anyone? Okay, so superconductor do not show any resistance. Okay, so that हाँ इसको हाँ बोलिए.
टेम्परेचर बिलो होने के कारण टेम्परेचर और रेजिस्टिविटी
नहीं, बट रेजिस्टिविटी तो 0 क्यों जाती है? सडनली 0 क्यों जाती है? ओके, मेटल में तो 0 जाके 0 जाती है. इसमें तो अभी जैसे हमें तो लो टेम्परेचर पे गया,
कंडक्टिविटी इनफाइनाइट हो जाएगी.
वही तो क्यों होगी?
Sir, suddenly electron goes to at particular temperature, electron goes to Cooper pairs.
Yes.
So
yes. Okay.
this goes to freezing.
So the explanation of superconductivity. Okay. The microscopic explanation of superconductivity was given by BCS theory. Okay. So BCS theory. Okay, so this was the number 3rd theory, BCS theory. Okay, BCS theory, which came in 1956. Okay, it was developed by Cooper, Bardeen, and J. Sniffer. Okay, so this is the microscopic theory. Okay, before that, the first attempt to explain superconductivity was by London brothers. Okay, London equations, which were able to explain this Meissner effect and zero resistivity. And after that, there were some phase-tension theory. Okay, that is called Ginsburg. Okay, Landau theory. Okay, that is microscopic theory. Microscopic of which is called phenomenologically theory. Okay, so and these equations are, there are two London equations which can explain electrodynamics of your superconductor. Okay, now I was discussing what BCS says. So the essence of BCS theory. Okay, the important point of BCS theory is we'll discuss in elaborate fashion later. So what BCS theory says? So BCS theory says when you reduce the temperature, your electron get condensed in ground states. Okay, so you have Fermi level and you have electron. So when you reduce the temperature, the electrons form pairs. Okay, the electrons form pairs, and these electron pair, okay, they are like a superfluid. These pair can move without scattering in your material. You are applying finite current, then also there will be no scattering, because these will be these Cooper pairs until you don't break this pair. If you don't apply the energy delta equal to Eg by 2, okay, these pair cannot be broken. So if you break this pair, you can destroy superconductivity. You can bring them in normal state. So superconductor is superconductor because here some of the fractions of electrons, okay, they are bind together and then form Cooper pair. Okay, so the Bardeen explained.
Sir, so why below temperature they pairs? It is a property or?
See, below TC is a material property. Na? Below TC, this is electrons. There should be electron repulsion. Okay? But at low temperature, via phonon scattering. Okay, via phonon, instead of repelling these electron, we can prove. Okay, by theory that the potential between these two electrons is attractive. Okay, when
below certain temperature.
At low temperature. Yes. So when electron energy is less than your phonon energy, okay, in that time, instead of repelling, that phonon can bind them together. Okay, the two electron who have spin up and spin down, okay, momentum k minus k, these electron can combine and they can move like a superfluid inside the conductor. Okay, so this is the main thing, this is theory. Now if I want to break superconductivity, how can I break superconductivity? If its material is in superconductive state, so how can I destroy superconductivity? Okay, so put the heading, how superconductivity can be destroyed. Okay, how बोलिए.
Now you have told us that electrons combine and behave as a Cooper pair. Means what Cooper pair means what?
Cooper pair means it's a bind electron pair. Na? Earlier electron was single. Now when you freeze them, like what happened in laser, both science in conduction, what happens? Okay, when you cool, they go in certain one state, ground state. Okay, so these Cooper form a coherent state. Okay, like you got laser action. Why do you get laser action? Why do you get high intensity? Similar type of phenomena happens when you reduce the temperature. This electron get pairs. Okay, and there is no scattering. Okay, like suppose many couples are dancing in the floor. Okay, so they have nothing to do with others, that they're dancing which each other, but they are not colliding with other partners. Okay, so same analogy is given here in BCS theory, that when your electrons are paired together, okay, they do not scattered. Okay, so we'll discuss this when we'll come to BCS theory. Okay, more about this. So so now, so at this point, I want to say the superconductivity is because of presence of super electrons, okay, or Cooper pairs. Okay, now I want to destroy superconductivity. Okay, so how superconductivity can be destroyed? How superconductivity can be destroyed? Okay, so superconductivity can be destroyed by three means. Okay, number one, you supply energy and you break Cooper pair. And you can break Cooper pair by providing thermal energy. So if you apply thermal energy, you can break this Cooper pair. Okay, that means you have TC, critical field. If you have temperature is critical temperature. If your temperature is more than critical temperature, automatically the superconducting sample will transit into normal sample. Okay, then you somehow increase their kinetic energy. Okay, kinetic energy means how you increase the current. You supply some current, you apply some electric voltage outside and increase the kinetic energy. Okay, so that is called what? That is called current density. Okay, if you increase the kinetic energy, okay, that is your current density. Okay, so JC is critical current density. If critical current density, if your current is beyond a certain value, then also it will become normal state. Okay, and the third is magnetic energy. Okay, so you apply a critical field SC, you apply a critical magnetic field, and you can destroy superconductivity. So these are three parameters by which you can destroy the superconductivity. Okay, so you know the current is equivalent to magnetic field. Okay, so when you have a when you current, you're applying current in a wire, okay, I, so it will produce its own magnetic field, which is equal to what? I upon 2 pi r. So current does same thing what your magnet does. Magnet, okay. So this is 3 parameters. So can I erase this one?
Sir, once.
So these parameters, okay. So basically this energy. Somehow we have to supply the energy. If we are supplying energy, we are breaking Cooper pairs. If breaking Cooper pair means you are destroying superconductivity. Okay. Now these parameters JC and SC, that depend, they are temperature dependent. Okay. So let me discuss that one. So now this magnetic field, without proof, let me write that your critical magnetic field SC is equal to H naught 1 minus T upon T square upon TC square. Okay. So when your T is equal to 0, okay, then you require SC equal to H naught. Okay, that means magnetic field you require to destroy superconductivity. When T is equal to TC, okay, then SC is 0. Obviously, when your temperature is TC, so automatically it become normal state, okay, because your sample is like this. Only TC it becoming superconductor, okay. Before that it is a normal conductor. So when you are reducing temperature,
Sir,
then only it is becoming superconductor. So you are applying temperature TC, then you don't need any magnetic field. Without applying magnetic field, you can bring sample into normal state. हाँ बोलिए.
so this equation from where
This we are not proving. This comes also from BCS theory. Okay, we are not proving here. Okay.
yes, sir.
So this proof is require very complicated mathematics. So we are not doing here. Okay. So similarly, current density JC. Okay. What IC upon area. Okay. And IC I told you what IC is what. IC is SC upon 2 pi RC. 2 pi R. Okay. So is this ये correct है क्या formula?
Yes, sir.
Or I'm writing opposite.
Sir, it should be I is equal to 2
Sir,
pi r.
I
Yes.
by 2 pi.
Yes, why that's why I'm asking. Okay. So IC will be what your SC 2 pi R, and the area cross section is pi R square. Okay. So if you solve this one, so JC will be okay. So R. Okay. So what will become? Pi cancel. So 2SC by R. Okay. This is formula for your critical current density. Now एक क्वेश्चन है कि मटेरियल का रेजिस्टेंस 0 है, तो आपको कैसे पता चल रहा? हाउ डू यू नो योर मटेरियल रेजिस्टिविटी इज 0? दैट मींस your material in superconductor current is flowing without any scattering, frictionless movement of charge carriers. How do you confirm?
रेजिस्टेंस जीरो है मतलब
How do you confirm that your resistance is 0? भी आपका सैंपल सुपरकंडक्टिव में आ गया, अब नाउ जीरो रेजिस्टेंस यू कैन नॉट मेजर ना, यू डोंट हैव एनी इंस्ट्रूमेंट व्हिच कैन मेजर द एग्जैक्ट जीरो रेजिस्टेंस. ओके, at most what we can measure up to 10 to the power minus 5 ohms. Okay, so how do you know that your sample resistance is 0? Can anyone tell? कैसे पता करेंगे? So yes, okay. So if you are superconducting current, okay, and you're applying some current when T is less than TC, this current should be keep on flowing without decay. Okay, that we can check. So we are in a superconducting sample. If we are applying any current, that current should be present in the sample without in decay for infinite time. Okay, and the time is given up to 10 to 5 power 5 years. Okay, and present हाँ वो हमेशा के लिए इसमें फ्लो होता रहेगा, करंट विल कीप ऑन फ्लोइंग इनसाइड the loop.
टोटल करंट कांस्टेंट रहेगा सुपरकंडक्टर.
Current constant रहेगा without decay. Okay, and this is actually tested. Now we have one sample last 29 years that is not decaying. Still they have some samples, some laboratory. They have flowed the current, and last it exists up to 27 or 29 years. So that you can say infinite time. हमारे लिए तो बहुत time है ना. So that saves our energy ना. Once you have current, that means you can create very strong magnetic fields, magnets with superconductors in this superconductors. So the ultimate test is you can measure the current, okay, and this current will be keep on moving up to infinite time, and that current is called persistent current. Persistent. Okay. So let me discuss some theories tomorrow.
Sir,
okay.
Sir, this current is gives the same magnetic field like ordinary current.
Yes.
और
yes.
डायरेक्शन लाइक मैक्सवेल्स इक्वेशन फॉलो करके ही देगा.
करंट वही मैग्नेटिक फील्ड का मैग्नीट्यूड वही रहेगा. ओके.
अच्छा. ठीक है.
So I'm stopping here. Okay. Tomorrow we'll discuss this London theories and this Landau theories. Okay. We'll see some more properties of the superconductor. Today we have seen just resistivity and perfect diamagnetism. Tomorrow we'll see how there is a band gap in a superconductor, how the free energy changes. Okay, and other properties we'll see tomorrow. Okay, so I'm stopping here. Thank you very much. Any question? So I'm stopping here. हाँ पूछिए.
जो
करंट अगर इनफाइनाइट होगा ना तो करंट डेंसिटी भी बहुत ज्यादा ही होगा. करंट फाइनाइट है, करंट इनफाइनाइट नहीं है. करंट तो फाइनाइट है. अगर करंट आईसी से ज्यादा हो गया तो वो तो वापस नॉर्मल स्टेट में जाएगा ना. करंट इन सुपरकंडक्टर यू कैन नॉट फ्लो एनी करंट. करंट शुड बी लेस देन योर क्रिटिकल करंट. Persistent. Okay, sir.
That is minimum. That is a less current. Okay, that current which is flowing in the superconductor, that is persistent current. That is less than your critical current.
सर ये जो कूपर पेयर फॉर्म होता है इसके साथ फोनॉन कैसे बाइंड होकर मतलब ये पोर्शन सर डिटेल्स में.
अब वो डिटेल में तो इतना तो समझना आसान नहीं है. that they can explain only some potential. They calculate some potential and they show when we are interacting with this phonon that the nature of this potential is attractive. Okay, that much they can prove with some theories. Okay. Okay, so that means they are binding together. Okay, and this BCS theory also only true for your type 1 superconductor. Tomorrow we will discuss what is type 1 and type 2 superconductors. Okay, so the material which has a critical field less than 30 kelvins, okay, SC, or that temperature less than TC less than 30 Kelvin, those materials comes in the category of your type 1 superconductors. Okay, type 2 superconductor you have very high this critical temperature. Okay, so your BCS theory only applicable for type 1 superconductor, not type 2 superconductor. Type 2 superconductor के लिए अब तक कोई theory बनी नहीं है. Still research is going on. People are trying to explain because there are many properties which they are not able to explain like they can explain for type 1 superconductors. Okay, so we'll discuss this tomorrow.
Whenever we say that the superconductors are perfect diamagnetism, follow. So, is it for the type 1 superconductor or type 2 superconductor, or whether for both?
Just type 1.
Okay, sir. Or sir, like in the Cooper formation, can we say that it is because of the lattice electron distortion?
Yeah, that's distortion. Yes.
Like whenever electron approaches a positive ion core, so it will distort that ion core and will acquire some positive charge, so that it can affect another.
So they have some correlations. Okay, they are binding together. They have some, say they are correlated. Okay, by some certain distance. Okay, if the distance is equal to the coherence length, then they are binded together. Okay, so there are two characteristics length in superconductor. One is called penetration depth and other is coherence length. Okay, so that these two lengths phenomena comes from GL theory. Okay, GL theory explains why there are two type of this length. Okay, so if your electrons are inside this coherence length, okay, in that condition their Cooper will not break. Okay, that is show the capacity. जितना बड़ा coherence length होगा उतना ही बड़ा उस material के लिए capacity Cooper pair की जो capacity होगी ज़्यादा होगी. Okay, you cannot break them. So if coherence length is high, then you require more energy to destroy superconductivity. Okay.
Okay, sir. Meaning that, sir, for the type 1 superconductor, they should follow that coherence and penetration wala formula, lambda by epsilon should be less than 1 wala.
So that should be applicable to type 2 also. Okay. Type 2, in the case of type 2, your coherence length is high. Okay. So your coherence length is bigger than your this one type 1. Okay.
Okay. Thank you, sir.
Thank you, sir.